Today I'm going to present the contribution called Trading Data Size and CNN Confidence Score for Energy Efficient CPS Node Communications. I am Issam RAIS, an Associate Professor at the Department of Computer Science at UIT, the Arctic University of Norway. This paper has been accepted in the main tracks of CCGrid 2020. So the Arctic tundra is a fragile ecosystem. We know that because it is a good indicator for climate change, as it is one of the most sensitive environment to climate change. The problem is that this region that is depicted in this picture here is hard to reach and hard to monitor. So we here are located in Norway. If you can see my pointer here, we are right here in Tromsø. And we have some nodes deployed in Varanger Peninsula, that's here. What we know about this place is that it is essential to do some observations. And right now, less than 1% of this region is observed. Thus, we need to have more recordings. It needs to be fine-grained, and it needs to be done for both the fauna and the flora. So the actual solutions that are deployed, one of them actually is Kuwait, our collaborators on the DEO project. And in this project, they have two main directions. The first one is done by satellite observations. And the second one, more coarse-grained, is standalone instruments deployed by humans. And in this case, by ecologists wanting to have some observations done on the ground. The main problem of the first one is that it is too coarse-grained. You don't know, for example, what is happening underneath the snow with the satellite observations. And the second one is that for the standalone instruments, it's that it doesn't scale. So we at the Distributed Arctic Observatory, we propose to have a distributed system of observation units, as we call them, to have a wider range of observations that could be done, but with more connection and more communication than what is actually done right now by Kuwait ecologists. To have more flexibility, we propose to have observations units that could be more general purpose. For example, in this picture, we depict the three main users. The first one is a DEO scientist that could have connections with nodes on the Arctic tundra to send, for example, updates or to send new information and new parameters to the nodes on the ground. The second type of user here is the Kuwait scientists that could, for example, look for data and retrieve data from OUs on the ground. Or you can even have the public that could connect to such a system to, for example, have some pictures about the Arctic tundra. So the Arctic tundra is a complicated ecosystem to monitor because obviously it has some restrictions in terms of resources. The first one is that there is a very limited network coverage with very strong variations. The second one is obviously the fact that the energy available at each node is very limited and that normal energy harvesting solutions won't work in such a context. And finally, working on the Arctic tundra and with nodes deployed on the Arctic tundra, we know that the manpower available to deploy such nodes is very limited for a very limited amount of time. You can't go up there during the winter, for example, because it would be way too dangerous and way too complicated. So in this paper, we propose a set of contributions. The first one is that we try to reduce the energy consumption of nodes sending data back to us only by leveraging the size of the data set. We combine a CPS, the DEO CPS, and a CNN to reduce the communication costs, both on energy, storage, and bandwidth usage. We document a significant reduction in energy for insignificant impact on the analysis of the data that is done afterwards. And finally, we document the relationship between image size and communication-related energy savings. So first of all, we are going to talk a bit more about the context and here the DAO project and what we are building and the specific use case that we are going to use here. Then we are going to talk about the analysis results as the ecologists use it. Then the uptime and energy savings that we have. And finally, a conclusion and future work. So first of all, an observation unit. So it is a device that we build to monitor the environment, but also to monitor itself, to know what is happening with the sensors, for example, or what is happening with the network, and to log what's interesting for the node to log. Ideally, we would like to have a common software layer, for example, to read the sensors, to store the data, to establish connectivity, and finally also to report the data. Here is an example of a prototype of observation unit that we have built. It is composed of a Raspberry Pi 3B here, 1 gigabyte of memory, a microcontroller, a Sleepy Pi 2 here, a bunch of sensors, a camera, passive infrared sensor to detect when there is something passing by, a humidity sensor, a temperature sensor. Obviously, it is not limited to that, but depending on the observation that we can do, such a unit can be generic enough to be just deployed as a node to help in the observations. It also has some network capabilities. Here it has a Wi-Fi bundle, a Bluetooth one, LoRa, and NB-IoT. And finally also an internal battery. Thus, with such a node, we can cover multiple ecological observations. A bit about the analysis of the images that we get actually from the Kuat testbed. So the CNN that is already implemented and used is using a single-shot multi-box detector. And for each of the images that we give him as an input, it gives you a list of predictions with a confidence score. For example, here for the image that we will have one line for this image with the category that has been detected. So here, red fox, and its confidence score, so 99.99% of confidence that it is a red fox. The CNN has been implemented in a previous contribution from the DAO project. It used the original Caffe Python implementation. The model has been pre-trained by using a set of 8,000 images annotated by Kuat ecologists with multiple species of animals, such as a red fox, eagle, raven, etc. And here is the model of communication that we have for these OUs. So here we are in the Arctic tundra for the N-1 OUs that we have here. They all generate some pictures. The assumption that we take here is that each OU can communicate with the machine that is running the CNN. And then this machine will give the results to the ecologists. But each OU generates pictures. These pictures are not used locally, but just sent to the machine that has the CNN running. And we assume that this is done with networks such as LTE or LTE Cat M1. A bit about the reduction of the images. The idea is quite simple. We have very big images, 2048 per 1536 pixels. And the idea that we have here is that either the OU reduces that size or rescales it. Does it rescales the image, or it takes a smaller picture and sends it directly to the CNN that has trained with bigger images. And again, the idea is to reduce the energy consumed while communicating these images. So here, for example, our red fox was at a scale of 100% per 100%, and it has been reduced to 70% per 70% of its original scale. Now a bit about the evaluation. The first dimension that is important to have here and to study is the impact of the image resize leverage on the confidence score that is outputted by the CNN. And here we are going to talk about all the detection that has been done. So this table represents the dimensions that is chosen. So from 10% of the original image to the original image, so 100% in terms of scale. Then we have the number of classifications that are found on all pictures. Then we have the delta in terms of confidence score, so the distance with the original detection that has been found. And finally, the size reduced, which is a factor that represents how much has been gained from reducing the images by the given scale. So for example, here, the scale from 10% to 90% reduced the size of the images by a factor of 48.79 to 1.45 of the original size image. So notice that we have a very low difference in terms of confidence score. And for a scale between 20% to 90%, the predictions are derived by 12% to 5% respectively. So the smaller the resizing of the image, the worse it gets in terms of image animal detection. Then we also need to take a look at the number of false positives and false negatives. Here again we have the dimension, the number of classifications. The number of false positive is between 95 and 35%. So reducing the scale of the image adds a lot of noise, obviously. And the same goes for the false negatives. We have between 75 to 12% of false negatives for the scales that goes between 10% to 90%. But what is interesting to notice here is that the false positive and false negative detections have a very low confidence score. So it adds a lot of noise, sure, but it's detections that have very low confidence score. Thus, even the CNN tells you that there is something there, but with a very low confidence score. And the fact is that the ecologists are only interested in, or trust enough, only the confidence that have a very high confidence score. They are only interested in plus 90 confidence scores. So that is why we also focus here on the confidence score that have a confidence score higher than 90%. So here the number of classification drop from 2000 previously to 94 here for the 10% scale to something that is equal to the 100% images. For the scale between 20 to 90%, the prediction for the confidence score that are above 90% are derived by 10 to 1%, including the standard deviation. And for the size reduced factor, it's about the same. For the scale that goes between 10% to 90%, we have 47 to 1.5 in terms of reduction. Concerning the false positive and false negatives, we have only one false positive, and it is detected only for the scale that is 10%. And for the false negatives, we only have 5 that are detected again for the scale that is 10%, so the smallest one. None of the others, even the 20%, have any false positive or false negative detected. Thus, there is a huge potential for energy savings here, with a very low impact on high confidence scores. So to evaluate this gain in energy and uptime, we implemented a simulator that aims at evaluating the cost in energy and in time to send the images from the nodes on the ground to the CNN application. And the interesting thing with the simulator is that it can evaluate multiple scenarios which were, well, almost impossible to find in real life. And we could also make the hypothesis to take the nodes out of the Arctic tundra. Thus, the aim of the simulator was to see the limits of this reduced size image leverage in multiple scenarios. And concerning the simulation result, we wanted to output how much energy it has been spent sending all the images that were generated by one node on the ground, and how much uptime has been saved for a given set of simulation parameters. The first one that we are interested in is the bandwidth. We want to have two scenarios. The first one is the Arctic tundra. So the extreme case that is our use case. It goes from 0.1 to 10 megabits per second. And the second one that is more general, what would happen if we had these nodes deployed in an environment where the coverage is good, 16.31 megabits per second. Then we also wanted to study two scenarios in terms of data set size. The first one is the bait cameras, which is the amount of images that were generated during a year by one node on the ground. And the second one is something that simulates a stream scenario. So an OU that will send constantly images to the CNN application. And finally, we also wanted to evaluate the power consumption, multiple power consumptions. The first one would be an OU-based, Raspberry Pi-based OU, and the second one with a microcontroller. So all these parameters are values that are either measured or extracted from previous literature. Either it is from our previous contributions or other contributions. And all these parameters permit us to have a wide range of scenarios when all these parameters are combined together. And in the paper, each of these combinations is a studied scenario. Obviously, we won't have time to cover everything here, but we will cover two cases, the worst case that we have seen and the best case. And in the worst case scenario, thus with, well, the worst case scenario in terms of energy benefits and uptime benefits is where the data is the smallest, thus the bait cam, and when the bandwidth is the highest. But what we were interested in is really how much time we would save, even if we have a good scenario in terms of usability of the nodes and the network. And here, with such a scenario, we would save about, well, between 3 minutes and 10 minutes, with a scale that goes from 10% of the original images to 90% of the original. And that would save us around 98% to 31% of the energy that is spent while sending the original images. And the best case scenario in terms of energy savings is when the data size is the biggest. So here the stream scenario with 12 gigabytes and with the bandwidth that has the lowest rate, so 0.1 megabits per second, which is a measured value that we had in the Arctic tundra during our experiments. And here the time saved is between 261 hours to 82 hours of uptime. So for a scenario like the Arctic tundra, the image resizing leverage is definitely needed to save energy. We have the same percentage of energy saved. That is explained in the paper. We have a proof that shows why it is like that. So please feel free to go read that section of the paper to understand the intricacies better of such a result. So as a conclusion, in this paper we have proposed and showed the positive impact of the image resize leverage. A wide variety of energy savings could be brought in such deployments or a negligible change in confidence score. Such leverage has a wide variety of potential usage, not just because there are a lot of images that are being produced and read by CNN afterwards, but also because such an idea could be extended to other usage than just paid camera and the CNN. It definitely is an idea that could drastically increase the lifetime of OUs on the ground, especially with our use cases or potential use cases that have similar characteristics. And all studied scenarios that have been covered in our simulation would benefit from this leverage. As a future work, we plan on implementing this leverage in a real deployment. We also think about other types of lossy and lossless compression for images, but also for other types of data. As we don't just generate images, some other filters on the data that is used could be interesting to have here also for us. So thank you for the attention. If you have any question, feel free to send me an email. Thank you.